Good morning. Here's your daily tech briefing for 2026-08-24. Today we're covering Java and Redis plus the Architect's Corner. Let's get into it. Java's string class has been a workhorse for developers for decades, and most of us reach for its index of method without a second thought. It's the go-to way to ask, where does this little piece of text appear inside a bigger string? The method returns the position of the first occurrence, or one if it can't be found. On the surface, that sounds simple enough, and the JDK documentation even claims it runs in linear time, meaning the time it takes should grow roughly in proportion to the length of the string you're searching. But a recent deep dive by Daniel Lemher shows that, under certain conditions, NestJS can actually degrade to quadratic time, which is a big performance surprise for many backend and DevOps engineers. Let's unpack what that means. In algorithmic terms, linear time is ON. You scan each character once and you're done. Quadratic time, ON times M, is far slower because you end up re-examining portions of the string many times. If you have a string that's a few megabytes long and you're looking for a pattern that appears many times, the difference between linear and quadratic can be the difference between a query that finishes in a few milliseconds and one that stalls your service for seconds. In a high-throughput microservice that processes logs, messages, or user-generated content, that extra latency can cascade into timeouts, thread pool exhaustion, and ultimately a degraded user experience. The root cause, as Lemher explains, is the algorithm that the JDK's string, index of uses for multi-character searches. For a single character, the implementation is a tight loop that checks each code unit in turn, essentially a straightforward linear scan. But when you ask it to find a longer substring, the JDK falls back to a naive approach that compares the target pattern at every possible offset, one character at a time, without any clever skipping. In other words, for each position in the haystack it checks whether the needle matches, and if any character mismatches, it simply moves one step forward and tries again. That is exactly the textbook quadratic algorithm for substring search. Why does this matter now? Modern Java applications often deal with large text blobs. Think JSON payloads, log lines, or configuration files that can easily run into hundreds of kilobytes or more. It's common to write code that loops over a string, repeatedly calling NestJS to pull out tokens, split sections, or validate formats. If the pattern you're searching for is more than one character long, and if the surrounding text contains many partial matches, you can unintentionally trigger the worst-case quadratic behavior. Lemher's benchmarks illustrate this with a synthetic example, searching for the string Ababa inside a long string of repeating characters. The naive algorithm ends up doing a lot of redundant work, and the runtime balloons dramatically as the input size grows. What does this mean for day-to-day engineering? First, be aware that NestJS is not a universal silver bullet for substring searches. If you're processing large inputs or running the same search inside a tight loop, you should profile the code. Simple micro-benchmarks can reveal whether the method is becoming a bottleneck. Second, consider alternative APIs that use more sophisticated algorithms. The Apache Commons string utils class offers index of implementations that internally use the Boyer-Moore-Horspool algorithm, which skips ahead based on the characters it sees and typically runs in linear time even in the worst case. Java 9 introduced string methods like lines and repeat, but it didn't change the core index of implementation. However, the JDK does provide pattern and matcher for regular expression searches, and under the hood, the regex engine employs a hybrid of deterministic finite automata and backtracking, which can be faster for many patterns, though it comes with its own overhead. If you can't bring in an external library, a practical workaround is to avoid repeated index of calls on the same large string. Instead, read the string once, perhaps converting it to a char array, and implement your own search using a more efficient algorithm like Knuth-Morris-Pratt, KMP, or Boyer-Moore. Those algorithms are a bit more code-heavy, but they guarantee linear performance and are well documented in open-source snippets. Another trick is to limit the search range by using the overload of index of that takes a starting offset. This can prevent the method from rescanning the same prefix over and over when you're moving forward through the text. The Java community has taken note. An issue was opened on the OpenJDK bug tracker pointing out the quadratic behavior, and there are discussions about improving the implementation in a future release. Some contributors suggest that the JDK could automatically switch to a faster algorithm when the needle length exceeds a certain threshold, similar to what the C++ std string does. Until such changes land, the safest path is to be explicit in your code about which search strategy you need. In practice, you'll see this problem most often in log processing pipelines, data ingestion services, or any system that parses semi-structured text. Imagine a log aggregator that extracts request IDs by searching for a known prefix like rec. If the logs contain many lines that start with rec, but also contain partial matches elsewhere, the naive index of could become a hidden source of latency. By switching to a library implementation or a custom linear time search, you can shave milliseconds off each parse, which adds up to seconds saved per million records. To sum up, the takeaway is that Java's string.indexOf is fast for single characters and for most small-scale uses, but it can fall back to a quadratic algorithm for longer substrings, especially in worst-case inputs. As a backend or DevOps engineer, you should profile any hot path that does heavy text searching, consider alternative libraries like Apache Commons string utils, or implement a more efficient algorithm yourself. Keep an eye on the OpenJDK issue tracker for a possible fix in upcoming JDK. Redora 0.3.1 landed on the open source scene this week, and it's the kind of incremental upgrade that can make a noticeable difference for anyone building services with NestJS and Redis. If you're not already familiar, NestJS is a progressive Node.js framework that brings a strongly typed, decorator-rich development model to the JavaScript ecosystem. It leans heavily on concepts from Angular, modules, providers, and dependency injection, so you get a clean, testable architecture without sacrificing the flexibility of plain Express or Fastify underneath. Because a lot of modern backend teams are already using Nest for their HTTP APIs, adding a solid Redis integration layer directly into that stack can shave off a lot of boilerplate. That's where Redora comes in. It bills itself as a Redis application toolkit for NestJS, essentially wrapping the low-level Redis client, one of the most popular Redis drivers for Node, with Nest-style providers, decorators, and configuration helpers. In practice, that means you can declare a Redis connection once in a module, inject it wherever you need it, and let the framework handle connection lifecycle, reconnection logic, and graceful shutdown. The toolkit also ships with ready-made abstractions for common Redis patterns, simple key value caching, pub/sub messaging, and even the newer Redis Streams API for building event-driven pipelines. The jump from the previous stable release to 0.3.1 is a patch bump, which usually signals a focus on stability rather than sweeping new features. The maintainers confirmed that this version addresses a handful of edge case bugs that surfaced when applications ran under heavy load or in containerized environments. One of the more subtle issues involved the way Redora's connection pool handled transient network glitches. In earlier releases, a brief hiccup could leave the pool in a half-closed state, causing subsequent commands to hang until the process was restarted. The 0.3.1 fix tightens the reconnection logic, ensuring that any dropped socket is promptly cleaned up and a fresh connection is re-established without manual intervention. For a production service that relies on Redis for session storage or rate limiting, that kind of resilience can translate directly into higher uptime and fewer random 500 errors that are hard to debug. Another tweak in this patch touches the TypeScript typings that Nest developers rely on for compile time safety. Redora now exports more precise generic types for the Redis client wrapper, which helps the IDE surface method signatures and return types correctly. While it sounds like a small developer ergonomics win, it actually reduces the risk of runtime errors caused by mismatched command arguments, something that can be especially painful when you're dealing with binary data in Redis streams or Lua scripts. The improved typings also make it easier to write unit tests that mock the Redis client, because the mock can now satisfy the same interface contract expected by the real provider. From an operational perspective, the update adds a couple of observability hooks that are worth noting. Redora now emits standard NestJS lifecycle events when a Redis connection is opened, closed, or encounters an error. Those events can be hooked into your existing logging or metrics pipeline. Think Prometheus counters for connection attempts, or structured logs that feed into a centralized ELK stack. In a microservices architecture, where each service may spin up its own Redis client, having a consistent set of metrics simplifies capacity planning. You can see, for example, how many connections each service is maintaining, whether any are lingering after a pod termination, and how often reconnection retries happen under load spikes. The toolkit also respects the environment variables that are common in cloud-native deployments. You can point Redora at a Redis Sentinel cluster, a standalone instance, or a fully managed cloud offering like AWS Elasticache, simply by adjusting the Redis URL or Redis host variables in your Nest configuration. The 0.3.1 release includes a small adjustment to how those variables are parsed, making it more tolerant of IPv6 addresses and of URLs that include a password segment. That change may seem trivial, but in environments where you rotate credentials automatically, say, using AWS Secrets Manager, having a parser that doesn't choke on the extra colon in a password string can prevent a whole deployment from failing at startup. If you're already using Redora in production, the upgrade path is straightforward. Because the version bump is semantically a patch, you can update your package, JSON to 0.3.1, and run a standard npm install or yarn add. The maintainers recommend a quick smoke test after the upgrade. Spin up a local Nest application, trigger a few cache reads and writes, and verify that the connection lifecycle events fire as expected. In a CI pipeline, you can add a health check endpoint that pings Redis through the Redora provider, ensuring that any regression is caught before it reaches staging. Overall, Redora 0.3.1 is a reminder that even modest, well-targeted updates can have a ripple effect across the development and operations workflow. By tightening reconnection handling, sharpening TypeScript typings, and exposing richer observability hooks, the toolkit makes it easier for backend engineers to lean on Redis without reinventing the plumbing each time. For teams that have already standardized on NestJS for their API layer, adopting Redora, or simply bumping to the latest patch, offers a low-friction way to get more reliable caching, messaging, and data streaming capabilities, all while keeping the code base clean and testable. If you haven't tried it yet, the documentation on the Redora website walks through a quick starter project, and the source code is openly hosted on GitHub, so you can inspect the implementation details or even contribute a fix if you run into a niche edge case in your own environment. Now, let's shift gears for the Architect's Corner. 5 minutes on real enterprise software architecture and system design. Imagine a product team that's building an AI-powered assistant for their internal knowledge base. The assistant needs to answer two very different kinds of questions. On the one hand, a user might ask for a precise, structured lookup. What is the SLA for service X? On the other, they might pose a more open-ended query. How do we troubleshoot intermittent latency spikes in our API? The first type of request is best served by a traditional key value or relational store, where you can filter on exact attributes. The second type benefits from semantic search. You embed the query into a high-dimensional vector, compare it against pre-computed embeddings of your documents, and retrieve the most similar passages. When the team started, they followed the pattern most organizations use today. They kept their operational data, service contracts, configuration records, incident tickets, in Amazon DynamoDB, a fully managed NoSQL store that scales to millions of reads and writes per second. For the semantic layer, they spun up a separate vector database, in this case an open-source solution running on EC2, and built a pipeline that listened to DynamoDB change events, pulled the updated record, generated an embedding with a large language model, and wrote that embedding into the vector store. In theory, it sounded clean, two specialized stores, each doing what it does best. In practice, the dual store approach quickly ran into three painful constraints. First, data duplication meant they were paying twice for storage and for the operational overhead of keeping the two systems in sync. A single typo in the change capture logic could leave the vector index stale, causing the assistant to return irrelevant answers. Second, the latency introduced by the cross-system pipeline, reading a change from DynamoDB, invoking a lambda, calling the embedding model, then writing to the vector store, added several hundred milliseconds to the time it took for a new record to become searchable. In a real-time support scenario, that delay was noticeable. Third, the operational burden of managing two separate services, monitoring their health, and handling disaster recovery grew out of proportion to the value they were delivering. The team's breakthrough came when they discovered that DynamoDB now supports native vector search. Instead of treating vectors as an afterthought, you can declare a vector attribute on a table, and DynamoDB will build an internal index that can be queried with cosine similarity or dot product metrics. The architects decided to collapse the two data stores into a single DynamoDB table that would hold both the operational attributes and the embedding vector for each item. The redesign started with a careful single table schema. Each logical entity, say, a knowledge article, was stored with a partition key that identified the tenant or domain and a sort key that encoded the entity type and identifier. Alongside the usual scalar attributes, title, author, timestamps, they added a binary attribute to hold the embedding vector. To enable efficient vector queries, they defined a global secondary index, GSI, that projected only the vector attribute and the primary key, allowing the query engine to scan the index without pulling the full item payload. Keeping the vector in sync with the source data required a reliable change capture mechanism. They leveraged DynamoDB streams, which emit a record for every insert, update, or delete. A lambda function subscribed to the stream, and for each change it performed 3 steps. First, it fetched the latest version of the item to ensure it had the most recent scalar fields. Second, it called Amazon Bedrock's text embedding model to generate a fresh embedding from the updated content. Third, it wrote the new vector back to the same DynamoDB item, overwriting the old binary attribute. Because the write happens in the same table, there's no cross-service latency. The update is atomic from the perspective of the downstream query. One subtle challenge was handling backfill for existing records that predated the vector column. The team ran a one-off batch job that paginated through the table, generated embeddings for each item, and performed conditional updates to add the vector attribute only where it was missing. They used DynamoDB's provision capacity with auto-scaling to absorb the temporary load, and throttled the Lambda concurrency to stay within the account service quotas. With the unified table in place, the Bedrock agent could now issue a single request to DynamoDB. The request combined a filter expression, say, service equals X and status equals active, with a vector similarity clause that asked for the top K most similar embeddings. DynamoDB's query engine applied the filter first, narrowing the candidate set, and then performed the vector similarity calculation on the remaining items, returning the best matches in a single round trip. The result was a dramatically simpler API surface. The application no longer needed to orchestrate 2 separate data sources, and the latency dropped from hundreds of milliseconds to the low single-digit range. Why does this matter for an enterprise architect? First, it illustrates the power of data unification when the underlying platform evolves to support new data types. By co-locating structured attributes and vector embeddings, you eliminate duplication, reduce operational complexity, and gain tighter consistency guarantees. Second, the pattern shows how to leverage managed services, DynamoDB streams, Lambda, Bedrock, to build an event-driven pipeline that keeps derived data embeddings fresh without building a custom messaging layer. The architecture is highly scalable. DynamoDB handles the read-heavy query workload, while the Lambda functions scale out to match the right volume, and Bedrock provides a pay-as-you-go model for embedding generation. Of course, the approach isn't a silver bullet. DynamoDB imposes limits on vector size, currently a few hundred dimensions, so if your use case demands very high-dimensional embeddings, you may still need an external vector store. The pricing model for DynamoDB's vector index is based on read capacity units that account for the similarity computation, so at very high query rates the cost can climb faster than a traditional key-value workload. Also, because the embedding generation runs asynchronously in Lambda, There is a brief window where a newly written item is searchable only by its scalar fields. If your application requires immediate semantic search on every write, you'd need to accept that latency or explore synchronous generation, which would impact request latency. Finally, and that's your briefing for today. See you tomorrow morning.